Let me just say, going on that, yes, certainly Saul and Jim and Mike Levy and others spent a lot of time in my office, and that's how I actually got to know Saul. He had made his discovery. Everybody there knew how important it was, and quite candidly that it was only a matter of time before the Nobel Prize would be awarded to him. But we were also focused, and he was also focused on going much further than that. But I'm not going to talk about that. I just want to give you a little introduction. Saul and I actually share some similarities. We grew up in academic families. We were both middle children. You know how hard it is on middle children, so you have to prove yourself. Much deeper than that, we both had Jewish mothers. He grew up in Philadelphia and ended up going to high school, 7th through 12th grade, in a school called Germantown Friends School, which was a Quaker school. And from that, he followed, in this good Jewish tradition, and went to a school founded for the training of Puritan clergy. It's called Harvard. And from there, and he got his PhD in 1981 from Harvard, and then went on to Berkeley. At Berkeley, he had a really wonderful thesis advisor, a person named Richard Muller, who, a very talented physicist, who gave his students a lot of rope and a freedom to do what they wanted. And Muller has a few famous graduates. One other is called known as George Smoot, who got a Nobel Prize in physics in 2006. Both Saul and Smoot were graduate students and postdocs and spent their entire careers at LB&L. There's where the similarity ends. I was a graduate student and a postdoc at LB&L also, but then I was going to spend my entire career there. That was the game plan. I then became an assistant professor, but I took a leave of absence for 19 years. Now, I got to tell you a little interesting story about his thesis project. Muller. Now, poor Rich Muller, his thesis advisor was Louis Alvarez, who was one of the really great polymath scientists of all time and a real legend at Lawrence Berkeley Lab, also a Nobel laureate, getting his Nobel Prize for a discovery of many, many particles using a bubble chamber, which was invented by another Berkeley Nobel laureate, but never mind that. But it turns out Alvarez also, with his son, discovered that what killed the last mass extinction was probably some cataclysmic event, a comet, a meteorite, something, that hit the Earth. But then someone noticed there were many other mass extinctions, and they were quasi-periodic, and there could be some Death Star out there, some invisible brown black dwarf that you couldn't really see, and some crazy orbit going back and forth and causing great tidal disruptions. And so Saul's thesis project was to find this Death Star. Does it capture it? Yes. He didn't, but he got good at looking for rare events, which he will tell you about. And Louis Alvarez, so poor is Rich Muller, two of his students are Nobel laureate, his advisor is a Nobel laureate, the advisor of his advisor a Nobel laureate, so they just skipped one generation, but everything else was okay. Because Louis Alvarez's mentor was none other than Ernest Lawrence, the inventor of the cyclotron and the founder of Lawrence Berkeley Lab. So this is a tradition that goes way back, and it's in this long tradition still going on today, where Berkeley Lab has trained as young career scientists, graduate students, postdocs, and first job, now over 32 by last count, young scientists went on to get Nobel Prizes. A remarkable tradition. Now, Saul will tell you about a lot of things, but there are two things I want to emphasize before I give him the last 5 minutes. One is that Lawrence founded something called team science. He began to put together teams of scientists that would work together across many disciplines that tackle problems that you just simply could not do in an individual small group. And it was that tradition of Lawrence, then amplified by Alvarez, who used to host weekly seminars at his home, at his so-called Group A home. And that has continued at Lawrence Berkeley Lab and, of course, has spread throughout the rest of the world. So the idea, and you'll get this from Saul's talk, and if I encourage you to read what he wrote, in that you can click on the Nobel website, and what he said at the Nobel banquet speech, which is, you're allowed 2 or 3 minutes, and it was a wonderful, wonderful speech. I'm not going to read you those words, but I would also like to say finally that there's another thing that scientists hope and pray for. You think we want to do something, to find something, to succeed in measuring something, to do something, but what you really want is to measure something where you get the wrong answer. And where, oops, that wasn't what was supposed to happen. And oops, it's better than we thought. And so with that, I'll give you Saul.
Good to be able to be here at the Department of Energy, and specifically I was hoping today. Perhaps that's better? Yeah. Ah. So I'm very glad to be here at Department of Energy, because partly I was realizing that so much of the sorts of work that I think almost all of us do, we never actually get to sort of see the products very often, and we're not, most of us are not architects and builders, and so we can't go back afterwards and say, oh, I built that thing. So I thought that on those rare occasions where there's a chance to tell a little bit what kinds of things the work that the Department of Energy does leads to, I should take the opportunity to do it. And I also want to do something particularly practical today with that in mind, which is I was going to see whether it's possible in this one story of being able to, because this is one of these times where the Department of Energy has been able to do so much to get to the point where we were able to win a Nobel Prize. It would be great if everybody here would be in a position to go home and explain exactly what it was that the Nobel Prize was rewarded for. And I think what's rare is to have something, such a fundamental physics story, be something that you can actually explain to people. So I don't think it's a terribly tall order for me to try to tell you guys what it will take for you to go home and tell your families, your friends, how it is that we've made this measurement. And you'll have to tell me later whether it worked. You can email me and complain, which parts didn't, But anyway, that's the idea. So I'll try. And you can start off, I think, the story in fairly good form, because the nice thing is that it begins with a question which I think almost everybody could imagine. The very first human beings walking outside at night, and I guess out of their caves at night, and looking up at the stars, and find themselves wondering, does it go on forever in space, and will it last forever in time? And it seems almost like what might define what it means to be a human being, that you would find yourself asking that kind of question as you looked up at the stars. And throughout almost all of human history and prehistory, there was really only one practical way to get an answer to that kind of question, and that was to ask the philosophers. And the philosophers actually had answers. So you could ask Aristotle, do we live in an infinite or a finite universe? And he could tell you. He said that we live in a finite universe, and he had actually a very interesting argument for how we know that we live in a finite universe. He points out that in an infinite universe, there's no place that's special. Every place is equivalent to any other place in an infinite universe. And then he says you can just go outside and do a very simple experiment. You can look up and you can see that there's this beautiful ball of stars, and we're right in the center of the ball of stars. And so clearly, the universe has a center, we're there, and so the universe must be finite. Now, obviously we laugh today, but if you think about it, it's a pretty sophisticated argument, and we didn't make huge conceptual progress on this for many, many, centuries, until actually, one of the moments that really made a huge difference was the beginning of last century when Einstein put down his theory of general relativity, which he probably did not do on a billboard. And he had and this gave us some more tools to ask this question in a more rigorous way. And he had a very interesting moment. I always pictured in, I think it was 1917 in the summer, where he took his theory of general relativity and he tried to apply it to the case of the universe. And there's a picture of him from 1917. I've always actually imagined him being very excited at that moment, but this doesn't really show it. So he quickly ran into a problem, which is that when he worked out his equations, he could get the universe to be sort of contracting in, and he'd get a universe that would be expanding out, but he just couldn't get a universe that would sit still. And as far as he knew, and as far as his astronomy friends knew, the universe was static. And so he did what I think many of us at some point in our high school physics lives have been tempted to do, which is to put in a fudge factor into the equations to make it sort of just balance out. And now when Einstein does it, it looks good. He calls it the cosmological constant, and he uses the Greek variable lambda. But it really wasn't actually that great a solution. It kind of made a universe that would just kind of teeter on balancing and standing still. And it was only within a dozen years that Slipher and Hubble made measurements, and we then realized that the universe really was expanding. And famously, Einstein called this his greatest blunder. I've been joking with my friends and saying that he had a chance. He could have predicted that the universe was expanding. He could have been famous, but he didn't. So what was it that that Hubble was seeing that made him believe that we have an expanding universe? Well, he was looking at these very faint, sort of fuzzy regions in the distant sky. At the time, they called them nebula. We now know that they were distant galaxies. And he was measuring their brightness and also their spectral features, these little lines in a spectrum. And what he found was that the ones that were further away, the ones that were fainter, which he assumed were the ones that were further away, had their lines shifted further and further to the red, which he assumed was a Doppler shift, just the same way a car horn sounds higher pitched as it comes towards you and lower pitched as it goes away from you. Similarly, if these galaxies are moving away from us, the lines get shifted towards the red in the spectrum of light as well. And so this was the evidence that we had an expanding universe. Now, at this point, when you're trying to explain this to your friends and family at home, I hope that somebody stops you, because the whole idea of an expanding universe is one that you really should stop at. It's I think, one of the more mind-boggling ideas. Now, when you talk about cosmology, you're in for mind-boggling ideas no matter what. I mean, just the ideas of these distances and the idea that the universe could go on forever, and these things are just mind-boggling. But an expanding universe should really bother you. It should be particularly mind-boggling. And the reason is because most people, when you hear the word expanding universe, especially when you've heard the terms Big Bang, it makes you think of an explosion. It makes you think of stuff exploding into space. And then you find yourself thinking, yeah, but isn't that space part of the universe? And what's expanding then if that space is part of the universe too? So I've been trying to come up with a different way of describing it. I think that's actually a very poor representation, a very poor way to be thinking of an expanding universe, even though all the popular science writers tend to fall into that trap, I think, of describing it as if it were an explosion. So I've been trying out a slightly different picture of the universe. So let me show you my conception of it. It's a somewhat simplified picture, because I can't draw very well. You're supposed to imagine that these are all galaxies, and if I were able to draw better, I would have been able to draw them going infinitely off that direction and infinitely off in this direction, and infinitely into the screen and infinitely out towards you. And you're supposed to imagine it really is an infinite universe. The galaxies go on forever and ever and ever in all directions, never stops. And that's supposed to be the picture of the universe today that you have in your mind. And the only thing that you should capture about this picture of the universe is that there's sort of a typical distance, typical average distance between the galaxies. Of course, in the real world, some are a little bit closer to each other, some are a little bit further, but on average, they're a certain distance apart, and it takes a certain amount of travel time to get from one to the next. Now, when I say the universe is expanding, all I mean is that we've pumped a little bit more space between all those distances, and so all the galaxies are now just a little bit further apart. And that's all I mean by an expanding universe. Just still infinite as far as we know, goes on forever in all directions, maybe all the same galaxies, just that there's a little bit more space between them. It takes a little bit more time to get from one galaxy to the next. And that's what you're supposed to picture when you say an expanding universe. So now there's nothing that anything's expanding into. It's still infinite. It's just that we're sort of pumping space in between the galaxies. If you go back in time, in fact, you start sucking the space out between the galaxies, things get closer and closer together. Eventually, you go far enough back in time, and everything's on top of each other. And that's really, I think, what we should have been describing as the Big Bang. But in some sense, we should have called it the Big Soup. Just that everything is sort of on top of each other. Could still be infinite, in this picture, up to the point where we don't know how to do the calculations anymore, when things get so dense that and then hot that our physics theories, need a little more than what we currently have. So that's the picture of an expanding universe that I think is helpful to have in your mind. It's a very simplified picture, but with that picture, I think you can now go back and ask that question about the fate of the universe in a slightly more rigorous way. Because now, when you hear about the universe expanding, you can start finding yourself asking, okay, but if it's expanding, is it going to keep doing it the same way? Is it going to expand at the same rate? And in fact, you might expect that all these galaxies, they all have mass. They might gravitationally attract each other, so maybe that could slow the expansion down. And if it's slowing, could there be enough stuff in the universe that it would actually slow someday to a halt and maybe collapse? So then you have a completely different way of asking about what is the fate of the universe, because you can go back and look back in time and ask, well, what's it doing before? Has the universe been slowing down in the past? And it turns out that we have ways of asking that question, and that's a measurable thing, which we don't have to go to Aristotle for this. So let me describe how we do that. First, we have conveniently enough, the universe has provided us a tool to make that measurement, and that is in the form of an exploding star, a supernova. And a supernova is a very bright explosion, because when that one star explodes in a galaxy of maybe 100 billion stars, that one star can be brighter than all the other stars put together in that one galaxy. So that's remarkably bright. So you can see them across vast distances across the universe. And when you can see things at vast distances across the universe, you actually get to see back in time, because it takes time for that light to travel to us across those vast distances. So here's the part where now, when you're explaining this to your family and friends, you might have to explain to them how you should think about how much time it takes for light to travel across the distances in the universe. I think most people are aware of the fact that light takes time to travel. At that point, I think you'll get across fairly quickly when you say it, when you tell it to somebody. But I think most people are not aware of how long it takes for light to travel across the distances that exist in the universe that we get to observe. So let me just walk through a few of these distances. First, the sun. If you ask, how long does light take to reach us from the sun, it's only about 8 minutes. So, someday if the sun were to go out, we wouldn't know about it for 8 minutes. Now we might notice it, And then, the nearest star the travel time is 4 years. So, we've orbited the sun 4 times since the light left that star that we get to see. That's relatively near. So that's okay, but it gets more interesting now as you get to the nearest galaxy of stars. Now you're looking at light. This light that we see in that galaxy left those stars there some 150,000 years ago. So the light left there around the time when here on Earth we have some of the first evidence for human culture. That's my attempt at drawing human culture. I'm not very good. But now it gets even more interesting as you look at the closest congregations of galaxies of stars. So that's the nearest galaxy cluster. Now you're looking at light that left those stars some 65 million years ago. That's when here on Earth the dinosaurs were going extinct. So, yeah, my extinct dinosaur. So, but that's nothing compared to these supernovae are so bright that that's nothing compared to how far back in time this supernova explosion occurred that we get to see today, which is the furthest we can see is 10 billion years ago. So that's almost 2/3 of the way. That's more than 2/3 of the way back to what we think was the beginning of what we've studied, the Big Bang or Big Soup, as I call it. And so if you think about it, it's incredible that this star exploded some 10 billion years ago, and it brightened in just a few weeks and faded away in just a few months. And that pulse of light's been traveling to us to tell us, that little bit of history from 10 billion years ago. And over all that time, eventually, the sun formed, and the solar system formed, and life evolved on Earth, and it evolved up to humans, and we got to learn how to build telescopes, and we built a telescope just big enough, just in time, and pointed in the right direction, and it fell into our telescope. I mean, so it's just remarkable to see that we're able to study just a bit of history now from something that far back in time. All right, so. And I particularly like this particular animation that gives you a sense of how vast these distances are. So it begins with an artist's rendition of a supernova exploding in a distant galaxy, but then it morphs onto real data, first from the Hubble Space Telescope and then from other telescopes. And you get a sense for how remarkably distant these events are. I mean, it's just very, 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 it's extremely... Anyway, it's so far away, and here at the end it shows you where this would be in the night sky. That you would see. I mean, it's just remarkable, how vast these distances are that we get now to see. All right, so now you need to explain that with these vast distances, that you are going to need to use these supernova as what we call a standard candle, where the brightness of the supernova will tell you how far away it is. So as you walk away with your candle, the further you get, the fainter it is. So that's a fairly straightforward concept. But someone might ask, why is it that the supernova are all the same brightness? And there you have to say that all supernovae aren't the same brightness, but there's one kind, which we call the type 1a, that we recognize by its spectrum, where when they explode, we think what's going on is that there is a dying ember of a star. This would be after our sun uses up all of its fuel. It'll be left dying off as a white dwarf, not bothering anybody, unless it happened to have a neighboring star orbiting around it nearby, and ours doesn't. But most stars in the sky do have some neighbor, and many of them have a neighbor that's reasonably nearby, and it can slowly dump mass from this other star onto this white dwarf over ages and ages until just enough mass falls on the star that you have a critical mass, and then you get a runaway thermonuclear explosion. And so that's the reason we think that these are triggered phenomenon and that they are actually at the same brightness each time. So now you can use these in that way as a standard candle, and you can tell how far away it is just by how bright it is. Now, there's one other piece of information that you need to know here, which is that when the supernova explodes, it sends most of its light in the blue wavelength, so it's a very short wavelength. So if you were looking at one close up and you didn't die, it would look mostly blue. But the supernova, the light then travels to us as the universe stretches, and in a universe that's expanding, anything that's not nailed down in the universe stretches just with the universe, and that includes this very wavelength of light. So by the time it reaches us, it's been stretched to looking red, and how red it looks tells you how far away. Tells you how much the universe has stretched in the time since the explosion of that supernova. Now we call this redshift, and in fact, in the cosmological story, it really is due to the stretching of the universe. Generally, most of it is not due to that Doppler shift that Hubble was talking about that I mentioned at the beginning. So in some sense, it's this amazing trick. It's a very direct measurement of how much the universe has stretched since the time when that one supernova exploded. And so you can imagine that a supernova in the distant galaxy explodes, and then as the light travels to us, beginning blue, and the universe keeps stretching, the wavelength stretches until by the time it reaches us, it looks red. And that's just how you read off the stretch of the universe since that time. So that's the entire story, and I think you can go home now and tell that to your... well, almost the entire story, because if you think about it, this tells you how much the universe has stretched since one time in history, the time when that one supernova exploded, which of course you know because you know how bright the supernova is, and how faint it is tells you how far back in time that was. But what you really want to do is find a series of supernovae of different brightnesses, representing different times back in history. So you find a fairly bright one, maybe that's from about a billion years back in time, and it tells you how much the universe has stretched since a billion years ago. Then you find another one from maybe 4 billion years back in time, and it tells you how much the universe has stretched since 4 billion years ago, and then another one from 7. And you just keep doing this, and then plotting the points, and you see whether or not the universe was slowing down enough to come to a halt. And that's really the measurement. And for a little while, I thought this was such a simple story that I could actually tell you this talk in the form of how to measure the fate of the universe with tools you can find in your own house. And so it almost works. So the idea is that you only need, nowadays, you just need a CCD detector. And nowadays, almost everybody has a CCD camera detectors in the back of their camcorders and their digital cameras. And that's good enough. Now, when we began the project, that wasn't the case. But now you all have those. You read out that digital image into your laptop computer. Nowadays, your laptop computers are fast enough to do all this image analysis that for us was heroics. Back when we were beginning the project, using all the computers we could. But your laptop's good enough, so you just connect your CCD to your laptop, and you go out and you put it onto your put it onto your telescope, and of course. That's where this idea didn't work, because the problem is, obviously, you need the biggest telescopes on Earth to measure these very, very faint supernova explosions. And so this is where the idea actually was a problem for us when we began the project, because these big telescopes, you have to apply to use them 6 months in advance. And you have to, and if you're lucky, you get 1 or 2 nights of telescope time to use that telescope. And and I was telling you before about how good the supernova is, how wonderful it was for this work. I have to tell you now that if you can use anything else for your research, you should use it. They're a pain in the neck to work with. The Type 1a supernova, they're rare. They only explode a couple of times per millennium in a given galaxy. And it's only so long you want your grad students to have to hang around. They don't give you any advance warning when they're going to explode, so you have no idea when it's going to happen. And they fade away. You have to catch them on the way up, of course, because you know how bright they are at peak, and that's where you have to calibrate off of. And so you need to catch them while they're still rising in just a couple of weeks. So it made a terrible telescope proposal to say, I'd like the night of March the 3rd, because sometime in the next 500 years a supernova might go off. And so in the beginning, a lot of the effort had to be turning this into a much more organized way of doing the science. And so what we ended up doing is developing these wide field cameras that would allow us to not just search one galaxy at a time for 500 years, but to search through thousands of galaxies in a night. And then you would have good odds of having, excellent odds of having half a dozen to a dozen supernova on that night discovered. And in particular, this telescope, if you take a time-lapse exposure for 10 minutes, gives you this image. And what you want to look at is not these distracting, beautiful-looking things in the front, but you want to look at these very faint little specks, these little blue specks all over the place here. Those are all the distant galaxies, about 4 billion years in this particular case, that you're seeing back in time. And those are the places where you want to look for the supernova. In fact, you were trying to find a little speck of light on one of these little blue specks that is a supernova explosion. And of course, that was the other hard part of the project at the beginning. You had to develop the image analysis software that would allow you to hunt through all of these little faint blue specks and find another tiny speck, which is your dramatic supernova explosion, if you can find it. So you got to the point that the computer could home in on this little region right here and tell you that this spot here was fainter 3 weeks before, and now it's brighter. And if you subtract this image from this image, you're left with just the supernova light. And so now you could start to guarantee supernova discoveries. We even figured out a way of timing this whole thing such that you could even say that you'd always find it just before new moon. So you could schedule the dark time of the month, which you need to use these very big telescopes to look for something so faint. We even were able to start saying what degree in the sky we would find that supernova on in that particular date. And that was important because if we want to use the Hubble Space Telescope, as we then started to do, they need to know not where to slew the telescope over in advance. And of course, we know what degree in the sky we would find the supernova in because that was the degree in which we looked. So that was fairly doable. But there you can see the white spot is the supernova, and the background smudge is the galaxy. On the ground, they all get blurred together. So this technique started to work. We started churning out a batch of supernova discoveries every time we went to the telescope. So we would do this every semester. You apply in these 6-month chunks. And over the course of a few years now, we now had built up a sample of some 42 supernova. And that seemed like a very auspicious number to us for those people who know the Hitchhiker's Guide to the Galaxy. I'll explain later. So we're now finally ready to get the answer to this problem of what is the fate of the universe. And you can make the plot that I was describing to you, using your supernova in the form of what's the sort of average distance between galaxies as a function of time. And possibility number one was that we thought the universe would be slowing because all the gravity of the stuff in the universe would slow it down. We just didn't know how much. And so one possibility would be that it would be slowing and slowing, but it would keep going forever and keep slowing down. And just to give you a more visceral feel for what that looks like, I made this little animation. So imagine that you're lying on your back, looking up at the sky, and I guess you have telescopes for eyes. And it looks a little bit like this. Everything is expanding away from each other and away from you. And they're expanding but getting slower and slower and slower. But this keeps going on forever. So that was one option. Option two is a little bit more dramatic. There you imagine that the universe has enough stuff in it to slow to a halt and then turn over and collapse. And that universe does have an end. We could call it the Big Crunch in that version, to complement the Big Bang. So this one is fun to look at. Everything expands away from each other, and then it slows down, and eventually comes to a halt, and then starts turning around and coming back in, I guess, at you. You start getting a little nervous. And this universe really does, have an end. So we thought this was going to be fun. I mean, because we had the data. We were going to get to see, which of these two lines we live on. And we figured whichever answer we got, it was going to be pretty dramatic. One case, you get this fiery ending. The other case, the universe actually is really infinite. And we've proven that the universe is infinite then. And we thought it was going to be great. And of course, what we found when we plotted the data points on this graph is the answer turned out to be none of the above. It was, the universe is just taking off. It's expanding now, but it's going to expand faster and faster, and then whoosh, pretty soon you're not going to be able to see any other galaxies. I've been arguing actually for funding agencies that this is our moment to do astronomy. This is our big chance to. Only a few billion years left, and then. So this was the result that you've heard about, and and that was such a surprise. And what it means apparently is that we. And let me show you. And let me show you what the data really looks like with real data points on that same plot. So average distance between the galaxies as a function of time. Here's today. We have nearby supernovae that don't tell you which line we live on, but they do show you that the relative brightness of the supernova tells you how far away they are, and that's how far back in time you're looking. And then the redshift. The stretch of the wavelength tells you how much the universe has stretched since that time. That's why you can plot these points on the graph. And then when we plotted all the points that we got these higher redshifts to see which of these lines we live on, whether it'll go on forever or turn over and collapse, we found that the data points missed all the lines, of course. And apparently we live in a universe that was decelerating way back in the past, but in the last half of its life it's been accelerating. And so that's what the real data looked like at the time. And there were two groups that were doing this. So that was the other thing that made a very big difference at this point. Another group started using our technique to find these and study these supernovae. And so interestingly enough, the person who was analyzing their data at that time, Adam Rees, was down the hill from where I was at Berkeley, just around the same time analyzing the data, calling the head of their group in Australia. And so we were all, independently seeing the surprise. We did not know, people were hiding the information from each other, of course, until we were ready to go public. And of course, there's the whole teams of people who were having the surprise together. This is one of the rare pictures of the two teams together. At this point, I always wanted to stop and remind people that although this is a popular image of science as being done by the lone scientists going off to the lab by themselves, it's really nothing like my experience of science at all. And almost all the science that I've done is in really close coordination with these amazing teams of people, all working nonstop together. And I sometimes say that if you want to do something social in your life, you should go into science. It's the most social activity that I know about, and I think people aren't aware of that. So I've been explaining that to when I go speak at universities, that if you really want to spend time with others, that's the job you should find yourself doing. Okay, so Apparently, we have a very surprising outcome of all this. Why is it the universe is expanding faster? We don't know. One possibility, and what we've been using as our placeholder for the moment, is this term called dark energy, which is that all of empty space could be pervaded by an energy that causes the universe to reproduce faster and faster between the galaxies. It's getting expanding at accelerating rate. And this energy would be something that we have not accounted for previously in our physics, and yet it could be almost 3/4 of the stuff of the universe. Now, that'd be remarkable, and of course, maybe even more remarkable would be if it turned out that that wasn't the answer. Maybe we actually need to modify Einstein's theory of general relativity, and we'll have to actually go back to something so fundamental and change our basic conceptions of physics. So whichever is the case, it's going to be remarkable. It's obviously triggered a torrent of papers from the theorists, and I was looking back on the archive the other day, and I realized that it's been averaging a little bit more than one paper per day for the past 12 years since the discovery. From the theoretical community on this, and if you and they come up with great names for these theories. I love like the phantom energy and big rip cosmology, and I can barely pronounce ekpyrotic universe. But I think it's fair to say, if you ask any of these theorists, do you stand behind your theory, and they will cheerfully admit to you, no, I'm just trying to expand the range of possibilities. I have no idea whether this is going to turn out to be the right answer or not. And they really say. They really put the question back to us, the observers and the experimentalists, and they say the ball is back in our court. We really need to give them a little more of a pointer as to what direction to pursue, and what is the most likely range of possible theories that might explain what's going on. And so we've not been sitting around. It's actually been it's been a pretty productive period despite this quote. And let me just show you some of what's happened. First, this plot with the data points from the two groups, between the 42 that we had and the other group's data, there was a little bit over 50 supernovae at the time when we first got this result. Now, if I, let's see, turn this plot around and flip it upside down and put it the way that the astronomers like to show it, the data sets have built up dramatically. Now there's more than 10 times as many, more than 500 supernovae on the plot. And almost every one of those 500 supernovae is better measured than almost any of those first 50 that we made that original measurement with. So there's been tremendous progress in improving these data sets. This is from a compilation that we just put together this past year from all these different groups, including many of these projects that we've been involved with as well. But it's also true that almost all of those, what did I show you, about 5,000 papers of theories that might explain dark energy, still any of those would be satisfied with this data set. This doesn't distinguish yet. And the problem is that you really need to make a very detailed measurement. In particular, if you, at the time when we were getting this result, we had to distinguish which of these lines we lived on. Now the data set looks tremendous. It's obvious which line we live on, although it gets a little ratty as you get out to these higher, further back in time. But now all those theories of dark energy that you have to distinguish are within the thickness of this green line. So we need something like 20 times more precision than we originally needed in order to be able to make this next step forward. Now, I won't have time to go into how we're going to do that, but I will say that we now know what it's going to take to make these steps. We've gone through each of the places in which error comes in, and I think when you start trying to tell the story, as I'm sure everybody will when you go home, you'll find that because it's such a simple story, people immediately start thinking of the obvious objections, what could go wrong. And they will think of some of these that I will show you. For example, how do we know the supernova, when they explode way back in time, are the same as the supernova that we see today? How do we know that the light isn't dimmed by going through dust? Just like the light from the sun gets red as it goes the atmosphere. It's getting dimmed. They probably won't think of gravitational lensing. That's where the light gets slightly amplified by being bent around intervening matter between us and the distant supernova. there's problems of the atmosphere that we're looking through. There are problems of the actual instrumentation, the telescopes, the filters, the detector response, if you don't get them perfectly calibrated. And all these things can contribute to this whole story of getting this precision improved by 20. But we actually have now done remarkable amount of work where we think we've identified what it takes to make each of these steps do the job if we have the right instrumentation. And in fact, some of the work that I won't be discussing goes back to reanalyzing the low redshift end, the very nearby supernova that are reasonably recent. And so there's a project that we've been working on called Nearby Supernova Factory, which has been very, very busy answering these sorts of questions. But I think it's fair to say that if we're able to build this next generation of projects, we're going to be able to take the measurements from nearby supernova and extend them all the way out with this factor of 20 times improvement. And so I think we're in very good shape for that next step in that direction. But it's not just supernova. We've actually, in this last 12 years, had, as a community, been developing a few other techniques now as well. And each of them is another short lecture where you can tell your friends about it, but I won't do it today. One of them has to do with moving forward in time from the hot and cold spots of the Big Bang that we see in the cosmic microwave background, and it overlaps the supernova, so we get two cuts at that curve. Another technique is almost orthogonal to these conceptually, where you're actually looking at that bending of light that I was mentioning due to matter between us and distant galaxies. And this technique has an advantage that when you use it together with the supernova and baryon acoustic oscillation, it can separate out possible changes in Einstein's theory of general relativity. So we can see which turns out to be the best answer. Is it a change in our theory of gravity, or is it this mysterious dark energy that pervades empty space? And so we have a lot of the conceptual tools now to approach this next problem. And it's been taken to the point that we have actual engineering diagrams for real projects which have now gone through all the prioritization processes, and we're looking forward to them actually moving ahead with real metal and glass, and seeing the things built. These are all the acronyms that show up for weak lensing techniques, for baryon acoustic oscillation techniques. These are satellite options that we've developed, and I think that when I look at these names, one thing that comes to mind in this context, just to get back to where we were at the beginning, is that it's interesting to note that almost every one of these experiments came out actually of most of the formative work came out of work that was done within DOE labs and university research. So it really is a very interesting DOE product, and so I wanted to finish for a moment just describing why it is that I think that the DOE approach to supporting science has been so successful, and why is it that there have been 2 Nobel Prizes now in the past 5 years in coming out of this kind of stimulated work stimulated by DOE. And I think there are a number of aspects of what we do at DOE in a DOE environment that's a little bit different than most funding models. And I want to call them out. I mean, one of them, one aspect is the fact that there's a willingness to take on large projects, and large in a number of different ways. Sometimes it's large in number of people that's involved. Sometimes it's physically large. You actually have to build large pieces of equipment, and it's a certain can-do spirit. It's also large sometimes in the time scales of exploration that it's going to take. So people often describe projects in terms of these short time horizons of when you have to write a proposal and when you're going to get your results. When we began this project that I'm describing to you today, we thought it was going to be a very hard project. We thought it would take us 3 years to get the answer. Now, 3 years in, we just sort of figured out how to do the project. And the answer didn't come until 10 years in. And I don't think anybody was disappointed at the end that it took us 10 years to get this answer. I think that's well worth 10 years. But science funding is rarely, it has that breathing space and that sense of purpose where you're going to keep working until you get the result when it's important to do. And so I think that's one aspect that DOE has been particularly good at. Another one is bringing together many different capabilities. So when we needed to build our first wide-field camera, first of all, the theorists who would give us the ideas of what we need to measure were down the hallway. The the opticians, the electrical engineers, the mechanical engineers, everybody was all around. The expertise for how you build an experiment was right there. And we were able to put these together in ways that I think are difficult to do in any other environment. And so I think this is something else that these national labs allow. And in coordination with the universities, it's sort of an amazingly powerful approach. Now, all that only works, of course, if you have people who know what they're doing with these resources. And we've been, I think, very fortunate that DOE, from the top down to the people who are on the ground, trying to get things done, have been able to help make these things occur. So, I mean, I'm very aware, for example, right now that our program manager, Kathy Turner, is somebody who is fighting ever since we were getting these results for giving us the flexibility in the room to making these next steps possible. And it's, and it's been clear that there's been one person after another who, in the course of the project I was describing, said, I know that they don't have a result today, and I know that's not obvious what this result, how it's going to fit into everything else we're doing, but this is important, and they kept that breathing space for the science to occur. And I think that's something that's just, that's important and unusual, and it has to be recognized. Then all that happens, I think, also if you have a real sharp sense of mission in the science. What is exciting science to do? And right in the heart of the DOE mission, and you get these mission statements like understanding how our universe works at the most fundamental level, and exploring the basic nature of space and time itself, and probing interactions between them. This is the kind of question that gets really smart people really interested, and doing all parts of the task. They get engaged by these kinds of problems, and they create things that you otherwise don't create. And I think that sense of going for a goal, making and doing an experiment, is something that DOE has really excelled in. It also meant that we, in this particular area, that we're able to pull together questions that come from all parts of these very fundamental areas, and what we call the energy frontier, the cosmic frontier, the intensity frontier. These are different parts of the fundamental physics program of particle physics. And what's interesting to note today is that so many of our most fundamental questions are being brought over from the cosmic frontier, the questions that are the biggest mysteries today in particle physics. Most of them are coming now from, brought in from the cosmic frontier into these other areas. And of course, they bounce back and forth as to which is asking the questions any given decade. But it is interesting that right now we're in a very unusual period where these questions are so much driven by the cosmic frontier in these most fundamental directions. So let me stop here with just one or two philosophical comments about what to me feels like an amazing bit of magic about the world. One is the fact that when you're doing these very fundamental questions, it's just remarkable to me that over and over again, when you've learned something very, very fundamental about the deepest underpinnings of how the world works that seems completely impractical, that somehow has ended up translating into something that allows us to do more in our world around us. And I think it's been the driver of so much of the most important developments of the world around us and our economies today. And so there's this very impossible to explain way in which, when you do these deep fundamental questions, you're actually building the next generation of technology and economies that we live in. So it's always worth repeating that, just because it's so hard to believe. But it always has happened. Every time we've learned something about how the world works, we've learned more how to use the world that we live in. And then there's also this other magical element that I just have to bring up here as well, which is that surprisingly enough, our brains, that evolved in the world, that seems so tangible that we walk through, seem to be able to understand this stuff, and that somehow, as every time we've been able to get a whole new data set, learn a new way of looking at things in a young field like cosmology still is, we've ended up being able to discover something new and fundamental about the world. And once more, I don't know how long that's going to keep going, that we're going to be able to keep up with what we see when we go out and make a measurement. But somehow, every time we've made these big steps forward in measurements, we've learned something amazing about how the world works. And so I'll just leave you, with this thought that we're at this very early stage in cosmology where every data set that we've come up with has taught us something new. We've just seen this data set told us that the universe is accelerating. Just a huge surprise. And I think we're now about to go through the next, I'm hoping, we'll build these next generation of instruments and we'll get this next discoveries. And I'm really looking forward to coming back and maybe being participating in the next ones or sitting in the audience and hearing the next DOE led Nobel Prize from these fields. So let me stop there and see if there are questions. I'm trying to see. Okay, there's a hand back there.
I'm not sure how to ask this question, but how does this work that you've described illuminate or fit in with this ideas about multiverses? Okay.
Yes. So among those 5,000 theory papers, there's been a whole series that comes out of this area called string theory, where they've been trying out some ideas where they ask, is it possible that what we're seeing here is a reflection of a broad range of possible universes that you could have, and then you statistically study what's the most probable kind of universe, and you say that if you can come up with a theory where the most probable kind of universe has these properties, then that counts as an explanation for what we see. And it's a bit of a stretch in thinking, of course, to imagine all these universes that have nothing to do with each other, and the only reason we know they're there is because we see one of the results of the statistics of what's the most typical kind of universe. At the moment, I would still say that probably most physicists are probably doubting whether string theory in its current form is going to be the answer, but it's perfectly possible.
If we ever build the James Webb Telescope on the NASA side, how does that fit in with your work?
So the Webb telescope, the JWST as it's called, is a much larger telescope in space. And it will make it possible for us to make some of those very detailed measurements of these quite distant supernovae, the ones that are back, in those plots that I was showing you, that are so far back that the data was getting rather ratty, as I mentioned. And those will help us recognize that those very, very distant ones, which ones of the very distant ones are the same kind of supernova as the matching ones that we see today, so you can make that distance measurement. So that will be one of the ones that has a good role there. I should mention that we've been working hard also on other space-based telescopes that have a broad field of view, which is in some sense better optimized for the mid-range of those very, very distant supernova that we would like to work on from space.
For a non-scientist, non-physicist like myself who would like to educate my wife on this topic tonight, and perhaps I missed this, but can you elaborate more on the kind of practical, tangible implications of this study, this work, in terms of what we do with it?
So this was touching on the topics that I mentioned at the very end here. Some of the story is this one where it's very hard to predict how, when you learn something fundamental about how the world works, how you'll end up using it. So nobody would have predicted, for example, that when Einstein's theory of general relativity started talking about clocks in relativistic motion, they're moving too fast, that it would ever have such a practical application as the fact that we're all using GPS every day now, and you couldn't do GPS unless you had that very fundamental understanding of how space and time work. And it's that way in which I think the biggest impact will be felt. Now, there's lots of other smaller impacts along the way. When you focus a lot of really smart people on these kinds of projects, they just invent things right and left. And so, for example, we've already, for these projects, invented, we took developments that were originally invented for actually the SSC super collider back when, we converted them to a purpose for another version of that CCD imager that I was talking about earlier. And that new technology is now going to be used for medical imaging as well. So there are these many side things that you wouldn't do if you were just trying to get somebody to work on a new medical imager. I don't think they would have thought of going that route. But there's something about having a very difficult challenge and putting smart people to work on it that ends up often making them invent things that you can then use for lots of purposes.
We discussed earlier the challenge of...
Actually, do you want the mic?
We discussed briefly earlier the challenge of getting smart people into this field, whereas previously a lot of the people ended up on Wall Street who should have come to Berkeley to be your successor. How do we entice young, smart people to go into science?
I mean, in some sense, this kind of topic, I think, is one of the best the best advertisements for coming into sciences. And I find that I've watched many students who begin pulled in to these very big, deep philosophical fundamental questions, and then find themselves fascinated by all the things they learn how to do as scientists, and of course go off into the world and work on lots of things as our science workforce. But there is something about these sort of deep fundamental questions, which is, I think, also just a great enticement into the field. And so I'm at the moment getting particularly interested in some of the questions of what will it take to bring more people into the field. Also, what will it take to teach a little more about how we approach problems as scientists to people who are not going to go into the sciences, because I think that that's actually also a very important part of our job as scientists. I think that there's many ways in which we ask questions of the world, and we do things that could be useful no matter what you apply it to, what science or any other area.
If I understood you correctly, I heard you say that we believe now that the universe rate of expansion was decreasing, and now the rate is increasing. Is that right?
So
what are the ideas on what's causing that?
That switch.
Yeah.
So what we believe, our current picture of how that worked would be that way, back in time, over 7 billion years ago, everything, remember, it's always been expanding. It's just a question of whether it's been expanding faster or slower. So if you go back in time, everything was closer together. It was a much denser place. That means that everything felt each other's gravity much more strongly. And we think that back in time, the gravity was the dominant player, and it did slow the expansion. It's just that as things became more and more dilute and further apart, the gravity became relatively weaker compared, the effect of the gravity was relatively weaker compared to this underlying hum of the dark energy that was just waiting to be felt. And then once the gravity became, ineffective enough, then the dark energy took over, and it became the dominant player, and now the universe started speeding up again, its expansion. That's our current picture, but you should remember that you should take it with a big grain of salt, since we don't know the answer. We don't know if really the dark energy is behaving the way in this simple way. By the way, I don't know. I was told at one point that we had to watch time, so maybe I should take just one or two questions. One, okay.
Is there a role for amateur astronomers to work in this field, or smaller observatories to make contributions to this, or is it you just need the big science to carry on forward?
Interestingly, this area is one of the few areas where amateur astronomers actually played a role in getting things going in the beginning. So when we were studying those, when we first recognized that type 1a supernova, the one that that's this triggered phenomenon that we use as our standard candle, the people who were finding those supernovae for the professional astronomers to study were mostly amateurs. There was one great example of a Reverend Evans who lived in Australia at that time, and would go out in his backyard every night and look at one after another galaxy, about 200, 300 galaxies that he had memorized what they looked like. And he was the most prolific supernova finder for a number of years before we actually started to turn this into a more robotic problem. Now today, I think that the game has raised so high in terms of the level of precision that we're after, that these sorts of problems probably will not be addressed by the amateur astronomers, except to the extent that we're still occasionally using amateurs in these crowdsourced ways where you send images, you put images up on the web, and anybody all over the world can help look through the images to find the supernova. And that actually has been quite successful. They get thousands of man-hours of time out of people just for the fun of it when they put it up. So occasionally that still happens. Well, thank you. It was a pleasure.